this video, let us look at few more properties of linearly independent vectors. We'll prove few propositions. First one is, let V be a vector space of dimension n, then any m linearly independent vectors can be completed to a basis of V, where m is less than or equal to dimension of the vector space V. Okay, so let us take a linearly independent set of vectors, say v1, v2, like that. There are m linearly independent set of vectors. Suppose these vectors are linearly independent, and I'll take up a subspace generated by these vectors. Let W be the subspace generated by these vectors v1, v2 dash dash vm. Okay, if this subspace is vector space itself, then what happens? M equal to n. I know that dimension of the vector space V is n, right? If my subspace W itself is V, then M equal to n, because subspace is generated by these m vectors, right? Therefore, if my argument, if W is equal to vector space itself, then m equal to n, and these are generating W, therefore they generate V also. Therefore I can say this is a basis for the vector space V. So the proof is over if subspace is equal to, subspace which I have taken is equal to vector space itself, right? If W equal to V, then M equal to N, and V1, V2, Vm form a basis. Of vector space V. Now suppose W is not equal to V. If W is not equal to V, okay, then I'll choose some vector, or I'll choose one vector, say Vm plus 1, which is in vector space V but not in W. Okay, we know W has got these vectors, m vectors, and this vector space V is of dimension n, and I know m less than or equal to n. So I'll take up one more vector which is not in W but which is in V. Vm plus 1 is not in W but it is in V. Then what happens? I can say that if this is the case, I can say that set of vectors V1, V2 dash dash Vm, Vm plus 1 are linearly independent. Why? Because, say, the reason is, why this is linearly independent is, say, how can I show that this is linearly independent? What has to be true when the vectors are linearly independent? If I take a linear combination with the scalars, then all scalars must be equal to 0, right? So let us check whether it happens or not. So I'm saying this is linearly independent because if there exists a non-trivial relation with the scalars from the field F, then non-trivial relation is written like this. a1 v1 a2 v2 dash dash am vm plus am plus 1 vm plus 1 is equal to 0. Now say am plus 1 is not equal to 0. This is not equal to 0 because I know that V1 to Vm are linearly independent. I have already taken it, so they are linearly independent. V1, V2, Vm are linearly independent. So till here they are linearly independent, therefore these are equal to 0. Right. Now this Vm plus 1 can be written as minus of Am plus 1, its inverse, into this whole expression A1 V1 plus A2 V2 dash 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 Am Vm. When I write Vm plus 1 as a linear combination of V1, V2, Vm, what happens to this Vm plus 1? It belongs to W because V1, V2, Vm are generating W. Therefore, any linear combination of these vectors implies that particular vector belongs to W. But which contradicts that we have taken Vm plus 1 belongs to V but not belongs to W. Therefore, I cannot choose any such Vm plus 1 which belongs to V but not belongs to W. So, which contradicts the choice of Vm plus 1. Therefore, I can say that there is no such vector which is in V but not in W. Okay, such so that they become a linear independent set. Okay, that is not possible. So let us look at one more subspace. Let us take one more subspace. Say why? Because why I have to choose one more? Because see here I know m is less than or equal to n. I have taken m linearly independent set now. Till n I have to take up and have to check each time. I have to take one more extra and have to check whether they become linearly independent or not. Once they become a linearly independent, then I can say it's form a basis. So let us take say W dash with the subspace generated by V1, V2, say Vm plus 1 now. Since I have taken their form, they are linearly independent, they'll become linearly independent up to this. So I'll take a subspace generated by these vectors now. If W dash equal to V, then what happens? N equal to m plus 1. So that this set of vectors V1, V2, Vm plus 1 is a basis for V. This becomes a basis for V since W dash equal to V. Otherwise, if it is not a basis for V, otherwise same argument, I'll take up one more vector which is in V but not in W dash. So choose Vm plus 2 which is in V but not in W dash. And I'll continue the same process. since the linearly independent set can have at most n elements, because I know that dimension of vector space V is n, so all the bases of V they have number of elements as n, right? So linearly independent set can have at most n elements. After finite steps, say I'm continuing this process, and I'll show that this vector, if it belongs to V, then it belongs to W also, W dash also, like that I'm proceeding. So after finite number of steps, say after this n minus m steps, because I have started from m plus 1, m plus 2, like that. So after n minus m steps, uh, the subspace generated by the vectors I'm getting is say v1, v2, vm. It was original one. I was keeping on adding vm plus 1, vm plus 2, like that till vn. Now what happens is this subspace generated by these vectors will coincide with the vector space V itself, right? So that what happens when this is a generating set, I can find say Vm plus 1, Vm plus 2, these vectors. These vectors such that this V1, V2, Vm plus 1, say Vn, they form a basis. Initially I had m linearly independent vectors, and I have chosen one more extra vector, and I'll check whether it is in V but not in W. I have chosen it like that. When I take it like that, this set of vectors become linearly independent because of this condition. So this element, I cannot say that it belongs to V but not belongs to W. So it has to belongs to W. So I cannot choose any such Vm plus 1 which belongs to V and not belongs to W. So that is not possible. So when it belongs to W, they form a linearly independent set and they form a basis now. Now the same way I'll continue, I'll take up one more vector and I'll say they form a basis. Like that I'll continue that process. After n minus m steps, I'm getting this subspace generated by these vectors, which coincides with the vector space V itself, which coincide with vector space V, right? Therefore, I can say that there exists these vectors Vm plus 1, Vm plus 2 up to Vn such a way that along with V1, V2, Vm, these vectors form a basis of V. So initially I had only this as my linearly independent set of vectors. So after n minus m steps, I'm getting these vectors, extra vectors, so that this is completed to form a basis of vector space V. So based on this proposition, I have few corollaries. If W is a subspace of V, then dimension of W is less than or equal to dimension of V. W is a subspace of V, then it says dimension of W is less than or equal to dimension of V. See, the same argument I'm using here to prove this. If I have, say, V1, V2 dash dash Vm as a basis of W, and this V1, V2, Vm it can be completed to a basis of V, right? Using this proposition can be, I'm sorry, can be completed to a basis of V. In fact, that basis is say V1 V2 dash dash Vn of V. Therefore, this m is less than or equal to n. That means dimension of W is less than or equal to dimension of V. Simply, it's a corollary to that proposition. There are few more. Suppose W is a proper subspace. W is a proper subspace of V if and only if this dimension of W is less than or equal to, less than, since it's a proper subspace, less than equal to dimension of V. See, first part, if W is a proper subspace of V and I have V1, V2 dash dash Vm as a basis of W, then I can say there exists at least one such element. There exists at least, say, one such element Vm plus 1 which belongs to V but it does not belongs to W. Hence I can say this set of vectors V1, V2 dash dash Vm plus 1 they are linearly independent in vector space V. We have proved that, so they become linearly independent in V. Therefore, what happens? Dimension of V is greater than or equal to this m plus 1, which is greater than dimension of W. So I can say dimension of W is less than dimension of V. This is if I take W as a proper subspace. The converse part is if dimension of W is less than dimension of V, then say if W equal to V, then I'll get dimension of W is equal to dimension of V, right? So I can say W has to be a proper subspace of V, right? If W equal to V, the same set itself, subspace is same as a vector space, then dimension will be equal, their dimension will be equal. Since they have mentioned it is less than the dimension of V, so W has to be a proper subspace of V. Therefore, W has to be a proper subspace of V. One more corollary is if I have a vector space whose dimension is 0, then the vector space has only one element, that is 0. Dimension of V is equal to 0 if and only if vector space V has a singleton 0. Next proposition is, if I have two subspaces generated by a vector space V, say V1 and V2, then dimension of V1 plus V2 is equal to dimension of V1 plus dimension of V2 minus the dimension of V1 intersection V2. So this is very important proposition actually. So let us prove this. I'm using the same concept to prove this, that is, if I have a vector space with dimension n, then any linearly independent set of elements can be completed to form a basis of V. This is the same proposition I am using to prove this proposition. Okay, so for that let us take let dimension of V1 intersection V2 be K. Okay, let vectors say U1, U2 dash dash UK with the basis of V1 intersection V2. V1 intersection V2. Now I know that even this is a basis, this is a set of linearly independent vectors. And I can even say that this set is a subset, linearly independent subset of subspace V1, because this whole set is a basis of this. Okay, so this is a subset of V1 vector subspace V1. So note that U1 U2 dash dash UK is a linearly independent subset of V1, so that I can add some vectors to this to make it a basis of V1. Okay, so that we can add vectors say V1, V2 dash dash Vm to this, so that the set U1 U2 dash dash UK with V1 V2 dash dash Vm is a basis of V1. Basis of V1. Now same argument I am applying to V2. Okay, so applying same argument to vectors subspace V2 means I am adding add vectors say W1 W2 dash dash Wn, so that the set U1 U2 dash dash UK with W1 W2 dash 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 Wn is the basis of V2. I'm sorry. basis of V2. So that what happens to the dimension of V1 and V2? Now dimension of V1 is, I had U1, U2, UK set of vectors. Along with that I am adding V1, V2, Vm. So dimension of V1 becomes K plus M and dimension of V2 becomes K plus N. Okay. Now V1 plus V2 is, in fact, we have learned about it, direct sum of two subspaces, which is nothing but it's a span of the vectors u1, u2 dash dash uk along with v1, v2 dash dash vm union with u1, u2, there is a comma, okay, I'm not putting it, uk along with w1, w2 dash dash wn. So v1 plus v2 is a span of these two set of vectors, in fact which is nothing but span of the vectors u1 to uk with v1 to vm and w1 to wn. So v1 plus v2 is span of these vectors. So I have to show that these vectors are linearly independent. See, if these vectors are linearly independent, then they form a basis, so that I can say this dimension of v1 plus v2 is k plus m plus n. So I have to show this as a linearly independent set of vectors. So to show the set u1 dash dash uk, v1 dash dash vm, w1 dash dash wn is linearly independent set, to show that I'll take up a non-trivial relation. Suppose I have a non-trivial relation, say for some ai, bi, ci belongs to the field F, a1 u1 plus a2 u2 dash 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 ak uk plus b1 v1 plus b2 v2 plus bm vm plus say c1 w1 c2 w2 dash dash cn wn equal to 0. I'm calling this as equation 1. I hope you can see. Yeah. So suppose this is a non-trivial relation. If I can show that all AIs, BIs and CIs are equal to 0, then it means U1, U2, V1, V2 dash dash, these set of vectors are linearly independent. So my intention is to show all these AIs, BIs and CIs are equal to 0. Okay, so let me take a vector, say V, which belongs to V1, okay, belongs to the subspace V1. Now this vector V, I know that V1 has a basis whose vectors are U1, U2 dash dash UK along with V1, V2 dash dash Vm, okay. So any vector in V1 can be written as a linear combination of these vectors. So let me write V as say A1 U1, A2 U2 dash dash AK UK plus B1 V1 B2 V2 dash dash BM VM. Since UI and VIs are basis of this subspace V1, therefore any vector in that can be written as linear combination of this. So when V is this, So the expression 1, in the expression 1, these terms can be replaced by v. So from that I can write expression 1 as changed to, this whole thing is v equal to, this comes to right hand side, so that it will be minus of C1 W1 plus C2 W2 dash 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 Cn Wn, right? So let me call this as expression 2. In fact, this is the linear combination of the vectors W1, W2, Wn. Therefore, this belongs to subspace V2 because these Wi's are in the subspace V2. Therefore, this belongs to V2. So now this vector V belongs to V1 also, and I've proved that belongs to V2 also. Therefore, this vector V is in V1 intersection V2. Since this V1 intersection V2 has a basis U1, U2, UK, since V1 intersection V2 has U1, U2 dash dash UK as a basis, say there exists the scalars d1, d2 dash dash dk such that this vector v is nothing but d1 u1 plus d2 u2 dash 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 dk uk. Let me call this as expression 3. So now I am using the expression 2 and expression 3. V is this when I say it belongs to V1, right? V is this when I say V belongs to V1. Now when I say V belongs to V1 intersection V2, and based on the basis of this V1 intersection V2, these are the generating vectors for vector V. So this is the linear combination for V. So now we have got two linear combinations, that is expression 2 and expression 3. So I'll club them so that I'm getting the expression d1 u1 plus d2 u2 dash 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 dk uk plus c1 w1 plus c2 w2 dash dash cn wn, which is equal to 0. One is the negation of other. Here v is negative, okay, in this expression v is negative of this, and here v is this. So I'll combine them and I'll write it, okay. So I'm getting this expression. Now I know that this u1, u2 dash dash uk and w1 dash dash wn are linearly independent. So di's are equal to ci's, which are equal to 0, okay. Since u1 dash dash uk, w1 dash dash wn is linearly independent, d1 equal to d2 equal to dash dash equal to dk equal to 0, which is equal to c1, c2 dash dash cn. All di's and cj's are equal to 0 for all I and j. The same as writing like this, okay. So now I got di and cj's are equal to 0. I have to prove k's are equal to 0, okay. For that, substitute this cj equal to 0 in expression 1. Expression 1 is this expression, bi's are equal to 0, ci's are equal to 0. So I'm getting this expression, right? So substituting this in equation 1, in expression 1. The expression 1 is becomes a1 u1 plus a2 u2 dash 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 b1 v1 plus dash dash bm equal to 0. I'm just substituting, say Cj equal to 0. If you want Cj equal to 0 in expression 1, I'm ending up with this. Since I know, again I'm using, why I'm applying this only, you will come to know now. Since u1, u2, uk and v1, v2, vm is linearly independent, we are getting ai's or al equal to 0. So a1 equal to a2 equal to dash dash equal to b1 equal to b2 equal to bm, which is equal to 0. Okay, why I am applying only this is I want to use this condition to make ai's are equal to 0. I can use this condition only when I have this full expression. That's why I am applying only Cj's are equal to 0, so that I can make all, say k I cannot use, I'll use some other suffix, say al equal to 0 for all l. So now I am getting all the coefficients are equal to 0. Hence I can say, the set of vectors u1, u2, uk, v1, v2, vm, w1, w2, wn is linearly independent. The set is linearly independent and is a basis for v1 plus v2. So now I have proved this basis for v1 plus v2. Therefore, what happens to the dimension of v1 plus v2? Dimension of v1 plus v2 is k plus m plus n. This is same as writing k plus m. I'll add 1k and I'll subtract 1k. Okay. So that this k plus m is nothing but dimension of v1 plus this is dimension of v2 minus k is dimension of v1 intersection v2. Hence the proof.